Good evening. Hi, my name is Larissa Back, and I'm a professor in the Department of Atmosphere and Ocean Sciences. And it's my pleasure to introduce our guest speaker tonight, Dr. Chris Bretherton. His title currently is the Senior Director of Climate Modeling at the Allen Institute for Artificial Intelligence. And he is also a professor emeritus at the other UW, the University of Washington, where he had faculty appointments in both the Department of Atmospheric Sciences and the Department of Applied Math. Chris has studied throughout his career cloud formation and turbulence and improves how they're simulated in global climate and weather forecast models. And recently, he's been leading the climate model development group at the Allen Institute for Artificial Intelligence in Seattle to use machine learning trained on global cloud reserving model output to improve the simulation of regional precipitation trends and extremes in climate models. Over the course of his career, he has helped lead field experiments and observational analyses and pioneered new frontiers in three-dimensional modeling of fluid in and around fields of clouds, including understanding how clouds will respond to and feedback on climate change. Computer code developed by his research group for simulating cloud formation by atmospheric turbulence has been used in the two leading US climate models. Chris was the lead author of the Intergovernmental Panel on Climate Change Fifth Assessment, or a lead author of the Intergovernmental Panel on Climate Change Fifth Assessment Report in 2013, chair of a 2012 National Academy report entitled The National Strategy for Advancing Climate Modeling, and a former director of the University of Washington Program on Climate Change. In 2012, he received the Jewel G. Charney Award, one of the two highest awards of the American Meteorological Society, and he was the 2019 AMS Horowitz Lecturer. He is a fellow of the AMS and AGU and a member of the National Academy of Sciences and Washington State Academy of Sciences. Please join me in welcoming Chris Bretherton. And I also want to mention quickly to stick around after the talk for drinks and appetizers and things like that. So you hopefully have drink tickets if you signed in. Thanks.
Okay, well, thanks, Larissa and Scott, for the logistics of organizing this. It's a pleasure to be here in Madison and to see all of you. I'd like to describe a tiny bit how I got into machine learning in the first place. As Larissa said, my background is actually in understanding the atmosphere through more conventional means, through taking models, through making detailed computer models, through trying to make climate models better by improving the way individual processes are represented in them. And I did that for decades, and it was great. And over that time, we have improved aspects of climate models, how our climate models now represent clouds better, for instance, than they used to. Our weather forecast models are more accurate. But it's been a slow process, and that process has always involved taking very complicated observations of the atmosphere or data about the atmosphere, trying to pipe it through the intelligence that we have in our brains, synthesize that into something that we can write into pieces of computer code, and then adding that computer code to very big, complicated models written in 50-year-old computer languages that actually help us understand future climate. And it's a very community-oriented process. What I did is what hundreds of other really expert scientists have been doing too. And the question is, well, that's all good, but are there other ways that we maybe could accelerate the development of climate models a bit more, take better advantage of all of the tools that we have to improve our ability to understand climate and climate change? So that's what took me into machine learning. Then I'd also like to start by showing you this picture, which is a satellite image off the west coast of the United States. It's interesting for two reasons. First, I think it just shows you the complexity of cloud fields in the atmosphere. You can just look at the different textures in this picture and the different scales of cloud formations and see that this is a very rich problem, and it's a very hard problem for simulation, for simulating weather and climate. It's also a hard problem for machine learning too. The other thing that this picture has in it, if you now focus on the coast of California at the right edge of the picture, is it has a strong storm hitting the coast of California. This is an atmospheric river event which brought a stream of moisture coming from the south, basically up against Los Angeles, where it rained about 10 inches and caused a whole bunch of flooding. And events like this are one of our major sources of rainfall on the West Coast. They're also one of our major sources of damages from flooding too. And they're a very important kind of extreme event that we think may grow more extreme in future warmer climates. And so these are the kinds of things that people want to understand. How is the chance of atmospheric river like this going to affect my backyard, or what my community has to do to make a bridge that's not going to be swept away, or how are we going to have to worry about our reservoirs and water supplies in a changed climate. So one of the reasons that there's been so much interest in climate is because we are entering a new era, often called the Anthropocene era. And that new era is characterized by our large emissions of carbon dioxide, mainly from fossil fuels, which is shown in the gray line here. So this is just showing the annual emission of CO2 by human activities, which was pretty small until about 1850 and has steadily risen since and continues to rise to this day. And sort of associated with that, carbon dioxide actually accumulates in the Earth system. It has a very long lifetime, has a 100-year lifetime in the atmosphere, but then it just goes into the ocean and the surface and lasts even longer there. CO2 concentrations have actually risen. So that's shown in the blue curve. This is, I think, as measured at Mauna Kea in Hawaii. And we've basically raised CO2 concentrations now by about 50% from pre-industrial levels. So from 270 ppm to something like 410 ppm. So basically that CO2 rise is the cumulative result of these CO2 emissions. And you can see that we're going to have to turn those CO2 emissions down. We're going to have to turn them around, bring them back to zero. And during that whole time, the atmosphere is going to continue to have increasing greenhouse gas concentrations, and we're going to continue to feel those effects. So the climate is kind of a big battleship steaming toward unknown waters, and we're going to have to not only try to mitigate that, to steer the battleship, but we're almost certainly going to have to adapt to where the battleship is taking us. So the most obvious effect of climate change is the global warming that's associated with increasing greenhouse gases. And this is just to show you we can really easily measure climate change. If we look on the global scale, although every year is a bit different, it's very systematic that over the last 50 years, the climate is warmed by something like 1.3 degrees Celsius, such that in 2023, relative to pre-industrial temperatures from 1850 and before, it was almost 1.5 degrees warmer. And that's considered by the IPCC and other sort of global organizations to be the sort of lower threshold for when climate change is starting to cause substantial damage to human and natural systems. So we're right on that threshold right now, and we're clearly going to pass it. So in this sense, then, the Earth of the past 50 years and of the next 100 years is surely going to be primarily under control of human activities and what we do. So it's not just temperatures, though. As the temperature warms, the atmosphere can hold more water. So for each degree Celsius, the temperature can get warmer. That's 7% more water that can be held in the atmosphere as water vapor. And so that would be about 10% in global average right now. And all of that water can be released by weather events. And so what that means is as the climate warms, precipitation events tend to get more intense. Flooding tends to get more intense. Droughts as well tend to get more intense. The period between rain goes up as well as the intensity of the rain that occurs. And so on all kinds of margins, there are a lot of extreme weather events that are exacerbated by a changing climate. So the one shown here on the left here is flooding. This is actually from that LA event I was showing before. Then we're seeing a drought in the middle, retreating ice as the climate warms and snow levels rise, and wildfires, another really big concern that Madison felt the effects of last summer. So we have these unprecedented extremes. You know, what's going to happen, and how do we know, and how do we prepare for them? So before we get into that, let's talk a little bit about weather and climate, because I'm going to talk to you about climate modeling, but all of the events I was talking about are actually weather events. So, just so that we're all on the same page about this, when I refer to climate, I'm referring to the statistics of weather. And statistics here means averages, extremes, the whole range of variation of weather over some long period of time, a period of at least decades. Typically, we use 30-year periods to define official climate averages in this country. That climate can change due to human or natural, what we call forcing. So one forcing is burning of greenhouse gases, which then releases CO2 into the atmosphere. We have other greenhouse gases like methane, which are partly being produced by human activities. And so all of those cause climate to gradually change. Now, weather is chaotic, and we can't predict weather more than a couple of weeks in advance. But climate, which is just the average of weather or the statistics of weather, can nevertheless be predictable. When we're interested in extreme events then, and we're interested in extreme events in a changing climate, they're involving unusual weather in a changing climate. And we can still predict how they're likely to change in terms of how often an extreme event is likely to change in a changed climate, even though we can't predict when an individual flood is going to occur. Okay, so I'm not sure how this will work, but just to satisfy the mathematician in any of you, let's get back to a very simple example of what I think demonstrates the difference between weather and climate, which is something called the Lorentz equations. So the Lorentz equations were named after a very famous atmospheric scientist, Ed Lorentz, who spent a lot of his career at MIT. And basically, one of the simplest examples we know of what's called a chaotic system. So a chaotic system is one that's very sensitive to its starting conditions. If you started in a slightly different place, unlike a pendulum, which just goes like this, a chaotic system will then go off and do something completely different, even if you change it just a tiny bit. So he made a set of 3 equations, which can be thought of as having to do with the flow of water in a tube, which is heated from below. And the 3 equations kind of describe the flow of water around the tube, whether the left is warmer than the right of the tube, because if the left is warmer, then the warmer fluid will tend to rise, and the colder fluid will tend to sink, and then whether the bottom is colder or warmer than the top. And by putting together equations for these 3 things, very simple equations, you can produce a very rich behavior. And in fact, simulating these equations is a classic kind of college classroom computer science project. I just wanted to show you, let's see how this works, a little video of the Lorentz system. So here, the different colors are just correspond to different time intervals. And what's shown is a 2-dimensional projection of this 3-dimensional set of equations simulated by a very simple computer algorithm. The important thing here is if you take a look at these curves, they never quite repeat. You tend to do cycles around these two centers, but they're never exactly the same cycles. And so they kind of fill in a whole range in space where at some point or another, the system is likely to be. Now, you can think of this, you can think of the evolution of this system as being like the weather. Okay, the weather is always changing. We're getting storms, then we get periods of clearing. We've got south winds and east winds and west winds. And then the curves that are filling in is like the climate. And so you can see that the climate here, the average of all of those curves is pretty well defined. They all kind of tend to, they're all tending to build into roughly the same average behavior, even though the system is chaotic and has weather and never does the same thing twice. So let's go back now to, sorry, I might have accidentally lost my PowerPoint here. It's unfortunate. No, it's good. Okay, there. Okay, so now I want to go and go back to weather and climate modeling. So I want to talk to you before I talk at all about machine learning about conventional weather and climate modeling, just so you can appreciate how it works and why machine learning is different. So conventional weather modeling was actually started around 1950, or computer modeling of the weather, by Norm Phillips, who at the time was at the University of Chicago as a graduate student. And so he made the first very simple weather predictions on one of the earliest computers built of vacuum tubes. And then about 15 years later, Suki Manabe on the right made what we would consider the first modern climate model. He was working in Princeton University at the Geophysical Fluid Dynamics lab. And so together, these two men basically sort of pioneered the fields of weather and climate modeling. Now, Suki Manabe actually recently won the Nobel Prize in Physics, or shared it, for his work. So this was an important development. And it led to a very long development of models that were ever more and more sophisticated and basically have helped us model weather and climate better and better. So, so these models basically are all written by taking equations that govern how air flows and how water condenses into clouds and rains or snows out, how radiation can be emitted by warm objects like the Earth or hot objects like the sun and interact with the atmosphere. And it encodes those in code that is written so that it tells you how the atmosphere will evolve on a set of grid points here, sort of indicated by that mesh on the right side. So you solve that set of equations, you step the state of the atmosphere forward a few minutes, and you keep doing that for weeks and weeks for a weather forecast, or for years or even centuries if this is going to be part of a climate model. So these models started very simple, but they got more and more skillful as the models used finer grids, which represent the atmosphere and the surface of the Earth and the mountains and the coastlines more accurately. And for weather forecasts, they also improved as a result of better observations, giving us a better starting guess at the state of the atmosphere. And for climate, those better observations have helped us make sure the physics in the model, the clouds and other processes are represented in a way that is accurate, that accords with our current scientific understanding. And so basically, this is making the models more physically realistic. What's shown on the right is how this evolution has gone for climate models. So climate models then started as just an atmosphere with a very simple representation of an ocean. Then the ocean and the atmosphere were both represented as fluids, which currents could move around in. So you had a Gulf Stream, for instance, off in the Atlantic. And then additional processes were introduced, like vegetation on the land surface, or sea ice, or chemistry. And so current climate models have many, many different interacting processes, which then act to define the response to, well, define the state of the Earth system and how it responds to climate change. At the same time, the models have been using a smaller and smaller grid spacing, so they represent the surface of the Earth more realistically. So they started with a grid spacing of 500 kilometers, and for climate models now, we use a grid spacing of anywhere from 25 to 100 kilometers. Now, there's the problem that finer grid spacing is much more computationally intensive. To decrease the grid spacing by a factor of 10 requires more than 1,000 times more computation. So there's a limited amount that one can do to make these models both have a fine grid and also run for hundreds and thousands of years. And that compromise determines what the grid size of the models is. Now, at the same time as these models, we actually can run experimental models of the Earth's atmosphere, which are actually run on much finer grids. And the much finer grids actually allow the model to make remarkably realistic looking depictions of the Earth's atmosphere. So on the left here is a 50-kilometer climate model. So what's shown in white is the clouds, and green are regions of precipitation, rainfall from those clouds. And you can see its pixelated character. In the middle is a model which has a grid spacing of 3 kilometers. So, you know, the Earth's 40,000 kilometers around. 3 kilometers means there's like 13,000 grid columns all the way around the equator. So this involves a huge amount of computation. But you can see that the cloud patterns from this model are recognizably similar to the ones from the satellite image on the right. Now, you're sort of 2 days into a forecast with that model, so actually the cloud features are partly the same because the model is actually basically making a weather forecast. But for instance, those 2 tropical cyclones in the middle, the spirals, they're really nicely represented by this 3-kilometer model. And the cloud patterns in the southern hemisphere are also looking very much like reality. So basically, models like this are actually called digital twins, often because they look so much like the real atmosphere that you might not be able to tell the difference. So they're beautiful, but they're also expensive. To do a simulation like in the middle on the on the Department of Energy's fastest supercomputer, Frontier, requires a day of the entire computer to run a year of the simulation. And that year of simulation would take the same amount of electricity as 300 US residents consume in 1 year. So you're not going to be wanting to do this the whole time. So these models are beautiful, they're very appealing, and we can't possibly use them for climate modeling at this point because it would consume more electricity than we have in this country. But just to show you how beautiful they are, let's take a look at a movie, which then can show one of these models in motion. So again, this is GFDL's X-Shield model, and this is a period of, I think, a couple weeks, and you can just see the cloud patterns that it produces. And again, if you were to look at a satellite image of the Earth's atmosphere, you really might have a tough time telling the difference. So again, this seems like this is a real scientific opportunity, but how can we actually use these? Oops, sorry, I have to get out of here. Well, okay, so now enter machine learning. And we're not there in terms of using machine learning with these very nice models, but we are getting toward that vision, and I'd like to tell you sort of where we are along that way. So I want to describe something which I was not personally involved in, but which inspired me and has happened recently, and then the variation on that theme, which I am doing, which is machine learning and climate. I'd like to start with machine learning and weather forecasting. So starting in about 2015, people, in fact, atmospheric scientists, got interested in the idea of trying to use AI to improve weather forecasting. And they started taking baby steps toward it. So this paper, for instance, was written by people who are from the world's leading conventional weather forecast center. And this was from, I think, 2017. And then they kind of designed a weather forecasting problem, which became known to members of the machine learning community and groups like Google, who then set some of their best machine learning engineers and scientists on the problem. And so there are more papers and more papers and more papers. And each one of these is from a different group that's trying to beat the forecast skill of the previous group. And so after about 7 years of this, now we're up to about 2022, 2023, we are now in the situation where we can make a 10-day weather forecast using a machine learning model that's trained exclusively on existing data about the state of the atmosphere and how it changes from one time to another time, say 6 or 12 hours later. We can make better weather forecasts using machine learning models than with any conventional atmospheric physics-based weather forecast. And this picture on the right shows that for one of these models, GraphCast. So basically the idea is that the horizontal scale is how far out your forecast goes in days, so out to 10 days. And the vertical scale is how big the error in the forecast is. And so being lower is better. And so black is the best conventional model from a place called ECMWF. And blue is the machine learning model. And at every forecast lead, it's doing better. So at this point, weather forecast centers have taken this quite seriously. And now ECMWF has hired its own internal group of AI specialists to take over and try and build their own machine learning model so they have control of it. So within the course of the last 2 years, this field is revolutionized. And that tells you something about machine learning, which is when it works well, it can really change things fast. It can change the complexion of things fast. I mean, another good example of that's familiar to all of you is ChatGPT. Okay, well, let's try and understand a tiny bit behind the machine learning magic. So these models are quite complicated, but actually in terms of lines of code and how a person programs them, they're actually a lot simpler than the Fortran models of hundreds of thousands of lines of code that we're used to using in this field. They're built on a couple of building blocks. One of the most important building block is the neural net. The neural net basically is based on taking inputs, so in this case those would be the yellow circles on the left, and then letting each input affect a whole bunch of outputs, the blue circles, which then feed a whole nother set of outputs, the green circles, which ultimately produce an output layer, which is the red circle. And the magic of machine learning is that you tune the sensitivity of all of those connections to make the output related to the input in a way that you can teach using a training data set. And what's particularly important to this is that the outputs are not linear functions of the inputs. They're fed through something called an activation function, a nonlinear function, that increases the ability of the neural net to flexibly produce any output, any desired output from any desired set of inputs. So they basically allow you to have this universal capability of fitting any function based on any set of inputs. And so they're very flexible to train, and that gives them a lot of power. Okay, so there we go. So we have these weather forecast models. They're more skillful than conventional models. Now we have climate. We care about climate, but climate's a bit different than weather in a couple of respects. So one of them is that the atmospheric component of a climate model, from a physics-based modeling perspective, it still could forecast the weather. It's still a model of the weather. And you just make that model run for hundreds of years, you gather its statistics, and that's the climate. That's one thing. The other thing, though, is that a climate model is trying to predict a future climate that we've never observed. So you can't necessarily train it on observations that we've already made, because now you're going to try and predict something that would involve extrapolation, and machine learning is very bad at extrapolation. So let's see how we tackle those problems. So our first problem here is actually shown here. So we took one of those weather emulators that we wanted to use and turn it into a climate emulator. And instead of running it for 10 days, we ran it for a bit longer. We ran it for 3 weeks. And what you can see, if you look after a while, is that, so on the left is our training data set. This is what we want the model to match. And what's on the right is what the emulator actually did. And you can see it starts by looking somewhat similar. And then there are these gray patches near the poles, which grow and gradually take over the simulation. So these are a numerical instability, which basically contaminates the entire simulation. And we actually find this is a very generic problem with these weather emulators. If you run them out for a few weeks or sometimes a few months, they typically don't stay stable. They don't continue to give you nice weather forecasts indefinitely. So we had to fix that. And actually, we were working with NVIDIA, who helped create this model, ForecastNet, and helped persuade them to implement a second version of their model, which was based on a slightly different architecture. And I'm not going to try and explain it to you in detail, but let me just say this about it. Basically, what it does is it says that if we want to understand changes in the weather, some things that happen vertically. So things like, for instance, rain falls out of clouds basically down. And some processes in the atmosphere are much more horizontal. So the wind blows air from cold places to warm places and warm places to cold places, mainly horizontally. So you have to have two kinds of machine learning, one of which sort of acts by columns and one of which acts across different horizontal regions. And the part that acts across different horizontal regions involves a different machine learning than the column-wise stuff. And the way that our approach, the approach that NVIDIA implemented with us works is it actually represents the atmosphere in terms of a whole series of sinusoids. If you know about Fourier series, then this is like Fourier series for the atmosphere. And then it does machine learning on those components. And it turns out that magically this particular architecture, for reasons we don't understand, doesn't have problems with the model blowing up. So it's much more suitable for climate modeling. So basically the idea of this approach in general is you frame making a forecast, making an atmospheric forecast, as basically like making a movie on the sphere. So you think about the entire atmosphere as being like a movie, only you're trying to predict things like temperature and moisture and winds at many different layers. So it's like a three-dimensional movie, but it varies in time, and you're just trying to predict the next frame from the frames you've had already. And so that's, in fact, the heritage of models like this, is thinking about video and image machine learning. And so other interesting features of the machine learning, it's a real curve fitting exercise. It has 200 million parameters that you have to train. So the model is figuring out how to optimize a ton of different parameters. And so to do this, it takes a lot of data. And so it turns out that it takes decades of data around the globe every 6 hours in order to train this model. So that's many, many gigabytes of data. So it's a big data problem. But in terms of the software, it's actually not that difficult. Okay, so I talked a little bit about the architecture of the machine learning. So how do we adapt a weather emulator to climate modeling? So one issue I mentioned is you can't train it on historical observations. And so basically the idea is, instead of training your model on observations, you actually train it to emulate an existing climate model. And you might say, well, that seems stupid. Why, I can just run the original climate model in all the climates that I want. I don't need the emulator. But the advantage is twofold. One of them is, it turns out that machine learning is insanely fast if run on the right hardware, so-called GPUs. And so you can take a model which basically does the same thing as your original model and now can do it 100 times faster. So if you want your model to run 100 times faster, you can emulate it. And then the other thing is that you can also emulate models you can't afford to run for climate. So for instance, I can take a model of the ocean at 2 kilometers, which I can only afford to run for a few years, or a model of the atmosphere at 3 kilometers that I can only afford to run for a few years, train my emulator to emulate that model, put those things together, and then perhaps be able to couple them into a machine learning model that I can afford to run for climate. So this is the kind of thing this is our vision of what we would like to do. We would like to take the very best atmospheric and oceanic models that we could make with the very finest grids that we could afford. And instead of trying to run them at the climate scales, which would take way too much computer time and electricity, we use them to make emulators that can then serve as the climate model and translate all the skill that we have in this model into something we can afford for climate. Okay, so let's just talk about where we've got to so far in that project. So about a year ago, we started building something I called the AI2 Climate Emulator. And basically, our first job was we wanted to train a climate emulator that could emulate an existing global atmospheric model, but do it accurately for a period of years or centuries, because the atmospheric component of climate models takes that long to, has to run as part of a climate model for centuries. And so what we did was rather than consider a changing climate, we started with a climate where you just specify the ocean to have its average seasonal cycle of temperature everywhere in the globe. You repeat that year after year after year. You can generate 100 years of training data using your atmospheric model, and then you can use that to train an emulator. And we trained emulators for 2 different global atmosphere models, one from NOAA and one from the Department of Energy, just to show that our process could work with multiple underlying reference climate models. And it takes a little bit of work to do this, but basically it's a pretty manageable task to train machine learning on this. It takes about 2.5 days to train a new version of our machine learning if we have a new version of this data set. And once you've done this, you can run a 100-year simulation with one of these emulators on in about 3 hours, while the model that we were emulating is about 50 times slower and consumes 1,000 times as much electricity, because it has to be run on a supercomputer. So now let's just show you we don't have the stability problems that we had before. So in this case, left is a reference model simulation, and what's shown here is the north and southward components of the wind. So blue is where the wind is from the north, and red is from where it's from the south. And these are actually from the first 30 days of an emulation. So the emulator starts with the same state of the atmosphere as the original model, but then because of the chaotic nature of weather in the atmosphere, it drifts away. But what's important is I couldn't tell you from just looking at one of these pictures which of these was the emulator and which was the original model. They both look equally realistic. There's no kind of artifacts in the model on the right, which is the machine learning emulator. There's no instabilities. So we've achieved our goal of having an emulator which actually looks like the original model in terms of its weather. So that was good. We're not necessarily expecting to achieve that easily. Furthermore, if you then ask about its climate, so now climate is the average of weather, and so one way of looking at climate then is to take the average of what you saw there and then compare it against the original model. So here, orange is our emulator and blue is the original model. What I'm showing you here is the temperature in the lower atmosphere averaged over the entire globe, just as one thing that I can compare between models. And in reality, in the northern summertime, the temperature tends to go up, averaged over the entire globe, because the northern hemisphere has lots of land that responds to summer, while the southern hemisphere is mainly ocean, and so its temperature doesn't change so much over the course of the year. So during northern summer, the temperature goes up in the reference model, as it should. That's the blue curve. Then it goes down in the winter, and this is showing 10 years of this. And then the orange is the emulator. And you can see that the emulator tracks the original model really, really well. And it has a repeating annual cycle. So, so this model passed this test really well too. Also of importance is how well you can emulate extreme events. So the idea is, you know, as I mentioned, sometimes an atmospheric river and dumps enormous amounts of rain there. And similarly, we have floods and droughts in other regions. So it's important if you have an emulator that the emulator be able to reproduce those extreme events. And that's maybe a harder task. So what's shown here is a plot of how often the frequency of occurrence of different precipitation rates. So each one of these is basically anywhere on the globe, you know, if the precipitation rate was around 200 millimeters per day, then it would show up, you know, in this part of the curve. So what you would like is that the distribution between very light precipitation events and heavy precipitation events in the emulator, which is the green, would match the reference model, which was in the black. And again, they're really similar to each other. So the emulator is able to predict extreme events too. Okay, so this starting emulator project works. So what's next? So again, remember the vision I was talking about. We want to emulate the whole Earth system. That involves coupling the atmosphere to the ocean. So then we need an emulator of the atmosphere. We need an emulator of the ocean. We have to be able to train them together. We then want to make the atmosphere one of these very fine grid atmospheres. The ocean, the highest resolution ocean we can afford. This involves more people and computing than we have at AI2. So this all involves collaboration. So a lot of what's going forward is we're trying to collaborate with other groups to leverage this idea into what it could be, which is, I think, a real way to revolutionize how we do a lot of climate modeling. And then once we've done that, then you have the additional additional challenge that you may think you're all skeptics about what you don't know, but put a bunch of scientists in a room. If you know faculty members, they're their own worst enemies. They love to criticize each other. And so basically convincing your colleagues who haven't yet, you know, swallowed the magic potion of machine learning that it's worth anything is a long task. And so you have to assume that that's going to be difficult too. So in particular, we don't want any hallucinations about future climate, because if we start making our planning decisions based on hallucinated ML climates, then that's not going to be very good news for machine learning. Okay. So one other thing I wanted to mention here that machine learning is good for, although this figure is kind of a confusing way to talk about it, is what we call downscaling. And so you have experts in your department here on your AOS department on downscaling. But machine learning, it turns out, is a very good way of taking information that we actually only model on coarse grids and turning it into more local scale information. So for instance, it's not so important in Wisconsin, but if you're saying California or the West Coast where there are mountain ranges, you know it rains a lot more over the mountains than it does in the valleys. And in particular, for instance, if you're interested in whether a particular watershed will flood that's in a coastal foothill, you need to know how much is it going to rain there, not how much is it going to rain over a 100 by 100 kilometer region around there. So typically we do what's called downscaling, and there are expensive and cheaper ways of doing it, but it involves a whole separate step and community of people, and in some sense often adds uncertainty into the process. And machine learning actually provides a natural potential way to do this, because what we could do is take these ultra-high global models ultra-high resolution global models we have, and use those. If they're the truth, we can then basically average information from the scale that they operate at, 3 kilometers, to the scale that climate models typically operate, 100 kilometers, and then try and learn the fine grid representation from the coarse grid. And this is what is called in machine learning super resolution. And so just to give you an idea of this, what's shown here is the coast of California. And what's shown here is a front hitting the coast of California actually in a fine grid model which has been coarsened to 200-kilometer resolution. So green and red here indicates the precipitation. So this is all the machine learning model needs to know. And then what it wants to do is figure out, well, what was the precipitation really at that time if you could have resolved it all the way down to the fine grid model resolution of 3 kilometers. And now you can see it's much more localized along the coast. There's coastal mountains that are enhancing the precipitation. At later times, the front hits the Sierras, and they show up as a band of precipitation. And it turns out that by looking at many, many atmospheric events, the machine learning is able to learn that when the low-resolution precipitation looks like this, that it actually can make this prediction, which looks very close to what the full high-resolution prediction actually was at that time. So it's able to do this task of downscaling very efficiently. And so that's something we're also very excited about. Okay, so that's pretty much it. The basic points I wanted to make first was, okay, well, physical weather and climate modeling is no slouch. Over the past 75 years, it's greatly advanced. We have great climate models. We have great weather prediction models. But with machine learning, we can make them even better. Machine learning is kind of a complementary tool, especially for climate. It relies on physical models of very high resolution that we think we can trust a lot because we use them as training data. But the machine learning allows us to deploy them much more widely because we can make models that are much faster, cheaper, and actually simpler to interact with, such that even someone who is a bit of a layperson could potentially interrogate these models to make better model predictions. So hopefully the idea is to democratize climate modeling. And then I want to thank the people and collaborators on the bottom who've really been doing a lot of the work that I've shown you here. So thanks. So I think we have about 10 minutes for questions. I can take the question. Well, do you want to take the questions, Larissa, or should I? But we are going to want people to go to the mics because we are streaming this.
Yeah, usually we allow students to ask questions first. I don't know if there's any students here that want to ask questions. That's what we do for our colloquium. Yes.
Okay. So yeah, if you are going to want to ask a question, why don't you go to the mic right now? Get in line, and that way we won't have to wait.
Hi, thank you for the talk. I have 2 questions. One of them is probably really dumb. First question, the dumb one, can you run these models locally for, let's say, a state for a short period of time instead of running it entirely for the entire globe?
You could, but it's a little bit of a different configuration. So for climate, it's more useful to have models that you run over the entire world. And so, but typically, the situation where you do regional modeling is this downscaling situation, right? So for instance, you don't necessarily, in order to understand details of precipitation, say, that are associated with fronts hitting the coast of California, you don't necessarily need to simulate the entire world at 3 kilometers. You can imagine you simulate most of the world at 100 kilometers, but then you have a much more detailed model that covers, say, the west coast of the US, which you then use for that purpose. Now, our view of this is that another approach is that you could do that, but another approach is you can use machine learning to your advantage, which is that you can sort of skip the second model entirely and then just run an emulator of the entire globe, which is quick to run and relatively easy to store output from, and then just use downscaling, the statistical machine learning downscaling to figure out what's happening at the fine resolution. And the downscaling there should be stochastic. It's actually generative form of ML that can produce a whole bunch of different possible weather states. And so, so anyhow, it can even deal with things like, but it can generate at least a possible realization of what the weather might look like.
I have one more question.
Yeah.
How do you measure the success of these models, and how much potential for improvement is there?
Well, okay, so right now we're measuring the success of the models because we are trying to emulate another model, right? So if you're trying to emulate another model, then that model is your, that's your reference. And so you measure the success of your emulator by exactly how closely it matches key features of the reference. So the features that we're interested in are things like the distribution of precipitation intensities I showed you, but also things like the spatial pattern of rainfall and snowfall. We would like to, if we average over a long period of time, we would like the spatial pattern of rainfall and snowfall from our emulator to look just like the original model. So those, we try and measure a whole variety of interesting statistics for the emulator and the original model and test that they match up well to each other.
Could you also speak about how much more potential for improvement there is?
Yeah, so there's potential for improvement in a lot of regards. So far, we have focused on the atmosphere. So we built an atmospheric emulator, but we know that we have a whole Earth system, right? We've got a coupled Earth system that all responds under climate change. So we have an ocean, which changes. We have sea ice, which is retreating as the climate warms. We've got ice sheets, which over longer time scales then respond to climate change. Vegetation, we've got all these other processes. And so any emulator which doesn't somehow either plug into a model which has those other processes or emulate those other processes too is incomplete. And so there's this much bigger project of how do you emulate the entire Earth system with all of these different processes. And that's a bigger project than my group is, and it's basically going to take the climate modeling community to decide as a whole that it wants to invest a lot more in this to make that happen, I would say.
Thank you.
Yeah.
Hey, Chris, great talk. And building on a larger picture here, my question is that further in the future, as the machine learning models get more frequent, like more common and also improve, would we still need to keep up with improvisation of our physical models? Because ultimately the machine learning models learn from a physical model.
Yeah.
So do we need the physical models' constant improvement to improve the machine learning models as well?
Yeah, I think we'll very quickly be in that situation where the biggest problem with the machine learning is that people don't trust the models that we're emulating. And I think there's a lot of reasons for that right now. So, for instance, a current problem with this whole approach is the problem of climate sensitivity. So, there are a couple of kind of big issues in climate. And one of them that I think we can kind of address right now is that different climate models tend to actually predict different sort of trends in precipitation in different regions. So for instance, some models in my area, the Pacific Northwest, tend to predict the Pacific Northwest will slightly moisten, have more rainfall. Some other models predict it will slightly dry. There's enough disagreement between models there to be awkward in terms of things like planning for hydropower. And it would be nice if we could bring those models together. And so I think some of what we're doing right now may already help with that. But another problem is that climate models disagree on how sensitive the climate ultimately is to greenhouse gases. So some models predict the climate is about twice as sensitive to greenhouse gases than other models. Those are kind of the extreme ones. And we can't tell right now which of these models is right or wrong for sure. They actually can all be fit to the historical record of climate change. And it turns out the main reason for that is they have different cloud responses to climate change. So some models, for instance, produce a massive meltback of low clouds over the oceans in a warmer climate that allows more sunlight to reach the surface, that allows the climate to warm even faster. So those models respond a lot to greenhouse gases, and other models don't do that so much, and so they respond less. And it turns out that those low cloud processes are no better represented in these 3-kilometer models really than in the 100-kilometer models we had, because they're due to little turbulent eddies in the lowest part of the atmosphere where the updrafts and downdrafts are only a few hundred meters on a side. And so we still don't have a great answer about that. So there's some problems that are, in order to do better, then we're going to have to make our models do a better job on those boundary layer clouds and eddies, which is a continuing challenge. So we're not putting physical climate modeling out of business. Same thing with weather forecasting. Although machine learning weather forecasting models can make better forecasts, they're reliant on a conventional weather forecast to make the initial state, the initial guess from which they start, because you have to bring data from many, many different sources together to make that initial guess. And the way you do that is you blend it with a weather forecast model. And currently, we can't use machine learning models as effectively as conventional models for that data assimilation purpose. So anyhow, yeah, so I'm really thinking of these tools as being complementary at this point rather than just like one replacing the other.
I have a related question. So first of all, I wanted to say that I found the results you showed to be very impressive. But given that climate models are an imperfect representation of Earth's physics, and machine learning is to an extent like a data fitting exercise, do you think there's any like long-term danger in relying on, like scientifically, and relying on machine learning, which is removed from the actual physics of the atmosphere?
Right, so we're going to have to gain some confidence, which at this point we don't necessarily have, that, for instance, if I were to consider this new class of models, like global storm resolving models, run at 3-kilometer resolution, that somehow that they either agree better with each other or they're fundamentally better for looking at changed climates than the models we use right now. Because otherwise, you're right, if you make an emulator of a model, you're not going to do any better in the model. And if that model is uncertain or it has biases, you've just emulated all of those biases. You haven't gained yourself anything. So, and it remains to be seen whether these higher resolution models are better. There's some things where I think we know that they're better. So for instance, for precipitation over land and over mountainous regions, because they represent mountains better, we can get more realistic precipitation distributions. But for clouds, I said, actually, early evidence is that the 3-kilometer models are almost as variable between themselves as coarser climate models. So that's where future model development is going to happen, is making these high-resolution models, or our best models, even better. So yeah, I mean, you can't, the problem with the prediction as a quote misattributed to Mark Twain is that you have to predict about the future, and you don't know what the future is, and so in the end you're stuck with your best guess, which is not always going to be imperfect. Yeah. Okay, remember the mic. Oh, is it time to go?
So we just had a few questions from our online audience.
Okay.
We had about 60 people tune in virtually, so shout out to everyone who watched the live stream. I guess for time's sake, we'll probably just do one of these. Nuo Chen wants to know, can the machine learning method make up for the lack of observations in the southern hemisphere and at the poles?
So no, I don't think so. I mean, right now the way we're using machine learning is we're emulating models. But if you think about how those models are improved, we use whatever observations we can to improve climate models like weather forecast models. And I think it is, though, a little bit of a myth, though, that there is a dearth of observations over the poles and the Southern Ocean. That's certainly true of in situ surface observations, but it's not really true of satellite observations. And in fact, a remarkable feature of the past 20 years is that 30 years ago, weather forecasts were much better in the Northern Hemisphere than the Southern Hemisphere, because we had a whole bunch of balloon observations in the Northern Hemisphere, nothing in the Southern Hemisphere. But now we've got so good at using satellite information to initialize our models, that our weather forecasts are just as good in the southern hemisphere, where you might think there's no data, as they are in the northern hemisphere. Because in fact, we do have data, and it's really good data, and in some ways, using that data over the oceans can be easier than using it over land. And so, so anyhow, yeah, so I would push back against the fact that that these are in fact data voids. The polar regions are sometimes more difficult because, for instance, it's hard to tell clouds over land surfaces and other issues like that. But even there, we know a heck of a lot from satellites and from remote sensing of the atmosphere everywhere. It's really hard to hide from a satellite.
Thanks, Chris, for your talk. It's quite a remarkable achievement that you've been able to get stability in a weather machine learning emulator over climate timescales. That's pretty cool to see. I was curious, though, in terms of thinking about the problem, it makes a lot of sense for a weather prediction to be, right, as you explained, sensitive to initial conditions. So going through one time step to the next to predict the next state of the atmosphere makes a lot of sense. But a climate, especially long-term climate, as I tend to think of as primarily a boundary value problem. And so the question is, why do you need to simulate all those steps in between instead of just training on, say, the climate of 2050s given climate of 2010s and the CO2 forcing, for example? Like, what do you gain from kind of doing the full emulation of the climate model versus just kind of going to the end step?
Yeah, I think that's a really good question, and the same question can be asked, well, why do you bother to predict the weather every 6 hours? Why not just predict the monthly averages, for instance, if that's all you care about? I mean, and I'd say the reasons are twofold. I think the most compelling reason has to do with extremes, which is if you're interested in extremes, you actually have to simulate them and sample them. And another related issue is, one way we're kind of conceiving of our emulator is as a part of an Earth system model, which might consist of other emulated or conventional components, all of which have to be constantly talking to each other. So if the components of your model have to talk to each other, they have to talk to each other on the scale in which they vary. And so, typically, for instance, in a Earth system model, we couple the components together every few hours or day. And so if you're not going to be able to do that if you only, simulate averages over years long. And then the other issue has to do with how your model interpolates between learned climates. So for instance, if you have information from a climate model about what goes on with a present day climate, with a doubled CO2 climate, with a quadrupled CO2 climate, and nothing in between, then how do you interpolate between those? And I think in some ways, the more that your interpolation is in terms of how it affects the weather and the possible states, as opposed to just trying to blindly, linearly interpolate, maybe the more defensible it is. But there, I think there's a lot of grounds for saying, I don't really know.
Thank you, Chris, for a great talk. I knew it was going to be good, and I was right. It's really interesting. I was thinking that we're here on the day after the eclipse. It was probably observed by more people than ever in history, and yet, and there was a time when predictions of eclipses were still pretty good, even though we had a completely false understanding of what was behind them. And here we've talked a lot about prediction, and I wonder if you can comment on the use of artificial intelligence, machine learning to help us understand more about atmospheric processes, because I'm sure there's places where that's going to come out. Certainly regular modeling does. You're a testament to that. We've learned more about how clouds work because of your modeling work. Is that promise also there for machine learning?
Yeah, I think so. I mean, you've got to maybe use it in a different way than we do right now. So one thing that we did as part of our modeling effort is, one of the problems with machine learning, at least the way that we've used it, is it knows nothing about the physics of the atmosphere. All it knows is, okay, this is what the atmosphere looks like right now. This is what the atmosphere looks like 6 hours from now. This is what the atmosphere looks like 12 hours from now. How do I, get from A to B to C? It doesn't know that that process is reflecting conservation of mass, momentum, water, that there's actual physics built into that. And in fact, so one can ask, does the machine learning even respect those conservation laws, for instance? And it kind of does. It turns out we instrument our climate model so we can kind of tell if it conserves things. And it's close to conserving things, but doesn't quite. So we actually build into our machine learning that it has to conserve air mass and water mass and so on. And that actually makes the machine learning a little bit better. So it does suggest that if we build a little physics into our machine learning, we can maybe make it even better. But another way that people use these models to gain understanding, even with regular models, is they use the model as a black box and then they prod it. So they say, okay, well, suppose we get rid of Greenland, or or suppose we add 4% to the solar constant or something like that. What happens? And then they try and analyze the response. And in that case, often the model is almost treated like a black box already. And you're just looking at, okay, if I poke it, what happens? How does it poke back? And a machine learning model can do that as well as anything else can. And if it can do it 100 times faster, it gets you to your conclusions a bit more quickly. So we have people, in fact, Libby Barnes at CSU is now trying to poke and prod our emulator to see if it does reasonable things when you, for instance, change the distribution of ocean temperatures to 1,000 years ago. And hopefully we'll have a community of people who kind of try and use the model, and we can gain some confidence in what it can do and what it can't do.
Thanks, everybody. I just want to remind you that there's a reception out this direction right now. So drinks, hopefully everyone got drink tickets coming in, and there'll be food as well, some food. So let's thank Chris again. And,